This is our fourth video for Unit 2, and it's on velocity versus time graphs. Here's what I want you to be able to do. By the end of this video, I want you to be able to make velocity versus time graphs, determine the acceleration using a velocity versus time graph, and describe the motion of an object using a velocity versus time graph. So far, we've been looking at position versus time graphs. Now, let's see what the difference is about velocity versus time graphs. So what does a velocity versus time graph show us? Well, it's really simple, and it's right there in the name. It shows us velocity versus time. So what you're going to see on a velocity versus time graph is on the y-axis, you're going to see velocity, and that's probably going to be in meters per second. And on the x-axis, you're going to see time. And that's probably going to be on seconds for this class. Let's take a look at a better one than what I drew. Now, you've actually seen velocity versus time graphs before. When we did our PhET Moving Man lab, you made velocity versus time graphs when you moved Abe back and forth. So, let's look at some different scenarios with velocity versus time graphs and come up with some rules. Be sure to take some notes for the OpenNote video quiz after this and to help you on your problem set. So the first scenario we could imagine is, what if Abe is just standing there? Well, that would mean that he's at rest. And if you think about it, what's the velocity of something that's at rest? It's going to be 0. So, if he's just standing there, his velocity is going to be at 0, and it's just going to stay at 0. Which brings us to the first rule of velocity versus time graphs. A velocity of 0 means that an object is at rest. Let's look at another scenario. Now imagine we had all of these different flat lines. On a position versus time graph, that would mean that an object is at rest. But think about what it's showing us for velocity versus time. Here, we have the scenario that we just drew on the last graph, where something is flat-lined at a velocity of 0 meters per second. What that means is that this object is at rest. Now think about what it's saying for this object. This one's flat at 2 meters per second. That means for the whole time of this graph, this object is traveling at 2 meters per second. If something has a velocity of 2 meters per second, is it at rest? No, it's not. It's moving at 2 meters per second for the whole time. So, all of these other lines are moving the whole time, because they have a number that's not 0. Now, why did I draw all of these lines all together on here? Well, let's think about it. This line, something is moving at 2 meters per second the whole time. If you compare that to this line, that means something is moving at 8 meters per second the whole time. Which one's going faster, 2 meters per second or 8 meters per second? Hopefully you're thinking 8 meters per second. If you did, you're right. So, what's this going to look like if something's moving faster? Well, if something's moving faster, that velocity versus time graph line is going to be higher. Now there's another line on here too. This one at -3. Do you remember what a negative velocity means? It kind of means the same thing as positive versus negative position. So negative, in our case of Abraham Lincoln, means you're going left. And positive means you're going right. So we've actually got a lot going on here. But what I want you to note is that these flat lines mean that an object is moving at a constant speed. And what constant means is unchanging. So, on a velocity versus time graph, a flat line doesn't necessarily mean that an object is at rest unless that flat line is at velocity of 0. Let's sort out all of the new rules that we learned on this slide. So, we learned that a slope of 0 or a flat line means that an object is moving at a constant velocity, or that it's not changing its velocity. We found that the faster the object, the higher the line, and we found that an object moving left will have a negative velocity, but an object moving right will have a positive velocity. You might want to pause the video and write these down, but I'm going to keep going. Let's look at this graph. This seems like a mess, and it's showing us 4 different lines. You should be able to interpret 2 of them right now. This one and this one. What's going on? This one is at rest because it's a flat line at 0 meters per second. This line has a constant velocity of 4 meters per second. So it's moving the whole time, but it's moving at the same speed. Now, what's happening to these? These lines don't have a slope of 0. So what that means is that they're changing velocity. And hopefully you remember from the last video that the change in velocity divided by time equals acceleration. So, what's happening to these guys? They're accelerating because they're changing their velocity. Now we can add another rule to our rules for velocity versus time graphs. So, if there is a slope to the line that's not 0, that would mean that an object is accelerating. And the steeper the slope means the greater the acceleration. So those are the 5 rules that I want you to know for velocity versus time graphs. And I know we went kind of fast. If you need more time, pause the video now to write down the rules, or go back and rewatch the first half. If you're ready to move on, let's move on and put those rules to use by looking at an example. So here's an example of something that's the movement of an object that's plotted on a velocity versus time graph. At first, you might be a little bit intimidated, but then just think about our 5 rules. Now that we have our 5 rules right here, let's see what we can figure out. During A, we see that the movement is a flat line and it stays at about 6. Which of our rules can we apply there? Well, this says that a slope of 0 means an object is moving at constant velocity. Well, that's happening at A, and that's happening at B, and that's happening at D. A velocity of 0 means an object is at rest. That's happening at B. The faster the object, the higher the line. Well, the highest line on here is D, so D is when the object is moving the fastest. An object moving left will have a negative velocity, an object moving right will have a positive velocity. A negative velocity is down here, and the line never dips below 0. So, our object that we're looking at is going to be moving right or not moving during this whole time. And here it says a steeper slope means a greater acceleration. And if we look at this graph, the only place where there's a slope that's not equal to 0 is during C. So this object is only accelerating during C. Now here's a weird spot right here that we didn't talk about. And that's like a very steep drop. So what's happening there is going from part A to part B, this object stops all of a sudden. So that's what you'll typically see in graphs that we'll use in this class, is where there's a very, very quick change in velocity instead of a gradual change. The reason we'll use these is we'll use ones like this where there's a rapid change is because they're much easier to deal with. Now let's dissect this graph a little bit further. So let's see what we can figure out just by looking at this graph. For part A, is it moving? Yes. How do we know? Because it's not at a velocity of 0. For part B, that means that this object is not moving, because that velocity is at 0. For part C, the object is increasing its speed, or velocity, so it is moving. And at part D, this is when the object is actually moving the fastest. The direction that's being moved, part A, since there's a positive velocity, it's going to be moving to the right. Part B, there's no velocity, so that means it's not moving, and it won't be moving in any direction. Part C, since there's a positive velocity, it's going to be moving right. And part D, also a positive velocity, so it's going to be moving right. Now, what's the actual velocity? Well, let's look at part A. That's about halfway between 4 and 8, so we'll call that 6 meters per second. Part B has a velocity of 0 meters per second. For part C, we can't really calculate a velocity because it's accelerating. We could say that it changes velocity from 0 meters per second to 8 meters per second, but we can't really calculate a velocity for that. Finally, for part D, we can see that the object is staying constant at a velocity of 8 meters per second. Let's take this apart a little bit more. We can actually figure out the total distance that's traveled using our special friend v equals d over t. So during part A, the velocity is 6 meters per second. We don't know the distance that's been traveled, but we do know that part A lasts for 3 seconds. So we could say d over 3. If we multiply both sides by 3, what we get is that there's a distance of 18 meters. So I'm going to put that in for part A. Now the displacement here would also be 18 meters. Since we're moving to the right for the whole time, the distance is going to equal the displacement. For part B, the object isn't moving at all. So its distance during part B is going to be 0 meters, and that will give us a total of 18 meters for A plus B. And the same for the displacement. So 0 meters just for part B, but the total was 18 meters. Now for us to figure out part C, it goes beyond what I want us to learn in this course. So I'm going to put an X through that, because we're not going to worry about figuring out the distance and displacement right here. But let's try to figure it out for part D. Again, using our formula, v equals d over t, we can see that the velocity during part D is 8 meters per second. We don't know the distance, but we do know that the time interval for part D goes from 8 seconds to 10 seconds. So that's going to be 2 seconds total. Now what we'd have to do is multiply both sides by 2, and we get a distance of 16 meters. Now remember, that's just the distance during part D. So, for the part that we can calculate, in this graph, it would travel at least 34 meters. Now you're going to get plenty of practice with this with your problem set. So, make sure to ask some questions, check the answer key, and make sure that you're solid on this, because we're going to be building on this in future lessons.